Hi, my name is Solomon, and in this third video in our IRROS series, I will be focusing on our 4 robot-specific repositories. So if you go to github.com/Interbotix in your browser, you will be brought to our Interbotix GitHub page. And the 4 repositories that I will be walking you through today are the Interbotix ROS Manipulators repository, the Interbotix ROS Rovers repository, Interbotix ROS Crawlers repository, and lastly, the Interbotix ROS Turrets repository. I will be starting out with this one. So click on it, view code. Okay, so before we get into anything, let me just, so we're going to look at this flow chart here. So you can tell which repository we're on because the one that we're on is highlighted in yellow, which is focused on our Interbotix ARMS repository. Now let's talk about the structure. So all of our robot repositories have a very similar structure. In the first repository, we're in the first level of the repository, we have different directories for whichever ARM we're using. So for this case, we have the Interbotix ROS UX arms, and this is code that I created that follows the IRROS standard for controlling the XARM 5, 6, and 7 created by UFactory. You should note, though, that they do have their own versions of their ROS packages, but I just adapted them to fit with our IRROS structure as more of a test to see if we could do it, which we could do. And then we have the Interbotix ROS XS ARMS directory, which contains all the ROS packages needed for working with our X-series robotic arms, which we have about 12. We have 12 different X-series robotic arms. So if we go here, we're going to see this second level of the repository, and this level contains the core ROS packages, as well as a couple other folders. So let's talk about that. The core ROS packages are the Interbotix XS ARM control ROS packages all the way down to this one. In relation to demo ROS packages, which live in the examples directory. So let's kind of go through this level of the repository. So we have the Interbotix XS ARM control ROS packages package, and as I mentioned in our ROS overview, in the IRROS overview video, this is the specific ROS package needed to get the robot up and running. So let's take a look at it. We go into it. We're going to see that there's a launch directory and a config directory. So if we go into the launch directory, we can go look at the launch file. And all it does is it calls the Interbotix XS ARM descriptions ROS package to launch the URDF, to load the URDF into the robot description parameter on the ROS parameter server. But besides for that, it also launches the ROS wrapper specific for the Interbotix XS SDK to control the Dynamixel servos. And it loads a specific motor config file so that depending on what ARM you're using out of the 12 ARMs that we currently have, it'll load the right motors, essentially. So that's the launch directory. And if you look at the config directory, that's where we have our motor config files. So we have one for the PX100, one for the PX150, Pincher X150, Reactor X150, Reactor X200. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the other 2 ARMs are the Widow X250 6-DOF, which we have a mobile version of, and the Widow X200 mobile version. We don't actually currently sell a mobile PX100 on by itself, but it is something that we have as part of our Locobot platform. So I included it there because if you're going to work with the Locobot platform separately, you would be, if you're working with a Locobot PX100 robot and you want to work with the ARM separately from the robot, you're going to launch this mobile PX100 motor config file. So what the motor config file does, let's just walk through that. We'd go with the Widow X200 here. That's my go-to one. So there's a few different parameters here. I'll just go through it quickly. We have port. So this is where you define where the port is on your computer that the U2D2 is connected to. In this case, I have a symlink called /dev/ttydxl that points to the U2D2 port. And the symlink is created by the udev rule, which is something that is that file is located in the Interbotix XS SDK ROS package. Then we have the joint order parameter. This defines the names for the joints as well as how they should appear in the joint state message. So it starts from waist, shoulder, elbow, wrist angle, wrist rotate, and gripper. So it pretty much starts from the ground up. Sleep positions. So this is an array of values that tell you that for each joint, what should the sleep position be. And this is a pose so that if you were to torque off the arm wouldn't collapse because it's already in a resting position. So the 0 goes with the waist motor, the -1.88 goes with the shoulder, the 1.5 goes with the elbow, etc. Then we have a joint state publisher config, and there's 3 different parameters within the joint state publisher variable. There's the update rate that tells you how often should the joint states for the different motors be published, and right now I have it set to a rate of 100 hertz, 100 times a second. So that's how fast the joint states will be read from the motors. And when I say joint states, I mean the joint position. So that's the present position register, the present, I think it's called present velocity, maybe, register, and the present load or present current register. Okay, so what the published states variable does is if it's set to true, then the joint state is published, and if it's set to false, it's not published, but you are still going to be constantly updating the code internally so that it has the most recent joint states. So that if you wanted to get the latest joint state, maybe by using the Python API that we have, you could do that. Then we have the topic name. This is what you want the joint state topic to be that the joint states are being configured on. So in this case, it would be called joint states. We have our groups variable. So this is where you can define an arbitrary name that will hold certain motors. So, and you can specify what those motors are. For the case of our arm, we have the waist, shoulder, elbow, wrist angle, and wrist rotate servos, because all of those are used in the inverse kinematic solver. As opposed to the gripper, which is not really considered part of the arm, all it's responsible for is opening and closing. So that would be considered a single servo that you would control. Then we have a grippers variable, and we're saying that inside the grippers variable, we have to specify which motor in our list here is the gripper. And we have one called gripper, but this is completely arbitrary. I could have called this like gripper Dynamixel or something. And then here I would write gripper Dynamixel, not gripper. So here, this is the horn radius, and the arm length has to do with the arms that come out from the servo horn, connecting the right and left fingers to the servo horn. And then the left finger and right finger parameters, that defines what those joints are called in the URDF. So then we have a shadows variable. So the shadows is used for any joint in our robotic arms that is a dual motor joint. So you would list what the second motor's name is that's part of that joint. So in this case, for the shoulder, in the Widow X200 arm, there are 2 motors in the shoulder joint. So the master is the shoulder servo, is called shoulder, and the slave, or the shadow, is called shoulder shadow. And that is specified in a list, because theoretically, if you weren't working with a robotic arm, or maybe you were working with a robotic arm and you wanted to have a really strong joint, you could have a 3-motor joint or a 4-motor joint just to give you more torque capabilities. So that's why it's a list here. But in most scenarios, it'll always just be one element, because majority of cases, you're only going to have a dual joint. Calibrate is true. So that just means when in a dual joint setup, even if you physically try to align the servo horns on both motors so that they are at the same position relative to each other, the encoder on one servo could still be a little bit off from the other. So when calibrate is set to true, what happens is the second servo's homing offset register is set so that the current position on the second servo matches the current position on the first servo. Sisters parameter has to do with motors that are a 2-in-1 type servo. So if you look at Robotics' store, they have some 2-in-1 servos. We don't have any in this arm, so we can skip it. And then we have a list. We have a config variable called motors. And inside this variable, we are going to list all the motors that we specified here by name. So these names that you give here have to match the names given here. So we have waist, we have shoulder shadow as well. So in this case, ID1 matches with the waist servo, ID2 matches with the shoulder servo, ID3 is the second motor in the shoulder joint, so it's called shoulder shadow, and it's not specified here because over here all we're specifying is the joint name, but it is specified here for it being a shadow of the shoulder. So all of these registers are EEPROM registers that you can set to have some initial values, and that's all I'm doing here. But anyway, the main point here is that this is the motor config file that I'm passing to the launch file, the XS arm control launch file that is being passed to the Interbotix XS SDK ROS wrapper so that it knows how to present these motors to a ROS user. Okay, so that is the config and launch files. Let's go back to the main directory here. So then we have the descriptions ROS package. And in this part of the directory, in this ROS package, we have a launch file that loads up the URDF to the robot description parameter. And it also can start up ARRROS for you, so you can visualize an arm in ARRROS. And all the STLs that are for each arm have their own directory here. For example, the Widow X200 meshes, you can see here for the base, the shoulder, the upper arm. You can even visualize them here. So that's the base, for example, for the Widow X200 arm. Okay, let's go back in here. So we have we mentioned the control ROS package and the descriptions ROS package. These are both core ROS packages because as an end user, you would build on top of them. They're not meant to be used by themselves. You're supposed to load them and then build on top of them. So another one we have is Gazebo. So again, you're supposed to create your own ROS node to interface with the Gazebo world. We have a Move It ROS package. That is also considered a core ROS package because you're not supposed to use it by itself. You're supposed to use like one of their move group APIs to make the arm move the way you want it to. We have a perception ROS package that helps. It uses a RealSense camera to locate different small objects on a tabletop surface and then give you the position so that the arm can pick them up and sort them by color or size, for example. But again, you would build on top of this package, like create your own Python script to use this ROS package to make the arm pick something up and then place it wherever you want. Then we have the ROS control ROS package, and this is not the same as the XS arm control package. This one here is specific for Move It, right? So Move It has to interface somehow with our robotic arm. So this Move It package actually built on top of the ROS control package, and this is a interface between the controllers, the ROS controllers that take in the trajectory output by Move It, and then this ROS control package here, like I said, takes in the trajectory that Move It sends, and it commands the robot directly through the Interbotix XS SDK. So besides for those core packages, we also have demo ROS packages. So the demo ROS packages are end user level ROS packages. This showcases how you, as an end user, would design your ROS packages. So some of these, like the XS Arm Dual, tells you how to use two arms in your setup if you wanted to work with two arms, but theoretically you could use the same ROS package, just edit it a little bit to to work with 3 arms or 4 arms. The Joy ROS package lets you use a PS4 controller to move an arm in Cartesian space. The Move It Interface ROS package showcases how to use the Move Group, C++, and Python APIs that Move It has to make the robot do some, to pose the robot in different poses. Then we have the PID ROS package. This is a way to play around with working with a controller that I made to move the arm based on PWMs or currents directly. Not something that you would, this is more for an advanced user. It's not something you would use to work with the arm. It's just a place to start. And then we have the Puppet ROS package, which allows you to move the arm. If you have 2 arms, so then one of them is torqued off and one of them is torqued on. And when you manually manipulate the one that is torqued off, the one that is torqued on will follow that motion as well. So those are some of the demo ROS packages. And then we have a Python demos directory. And inside that directory, we have a bunch of Python scripts. So if you're not familiar with ROS, but you still want to work with the arm, you can treat the robot as an object in Python. And that way, if you're a researcher doing some machine learning problem or computer vision problem, you can work with the arm this way without having to worry yourself with all the lower level ROS packages stuff. There were 2 other directories I wanted to show you. So we also have an install directory. So that directory contains some bash scripts that you would run to get all the necessary ROS packages and code on your own personal computer to work with the robot platform. And there are instructions on how to do that in the README. And then we also have this cat can ignore file. So like I mentioned in a previous video, this is so that, let's say you only wanted to work with our Dynamix line of arms, the install script would remove this cat can ignore file. But let's say if you're only working with a Dynamixel-based arm and you were not working with the Universal Factory arms, you would keep the cat can ignore file here. You would not delete it, so that when you would run the cat can make command in the Interbotix workspace, all these ROS packages would be ignored, and you wouldn't have all these dependency packages to work with this arm installed, since you don't need it anyway. So just to show you the IRROS flowchart for our Dynamixel-based arms, go down here. So we have the robot computer connects to a U2D2, which connects to the Dynamixel servos. And then in some of our example ROS packages, we have a RealSense camera, like for the Perception ROS package. And then we also have a PS4 controller for our Joy ROS package. So that's in the hardware layer. In the driver layer, we're using our custom Interbotix XS SDK ROS wrapper to control the Dynamixel servos. And we are using the RealSense ROS package to work with the D415 RealSense camera for our Perception ROS package. And we also have the Joy ROS package to work with our PS4 controller controlling the arm in Cartesian space. Then we have the control layer, which, like I showed you before, it launches the node in the Interbotix XS SDK ROS package to work with the arm. It passes in that motor config file I mentioned earlier, and it loads up the URDF to the parameter server. And then in the application support layer, we have our Python modules to do IK for the arms, or we have a base version of the ROS control package that interfaces with MoveIt that has lower level code. And then we have some base code for the MoveIt interface package. So even though we have, like I showed you before, we have an Interbotix XS ARM ROS control ROS package that is located in this repository, there's no code in there. It's just config files specific for the Dynamixel-based arms. But it launches a node that is within the ROS control package located in the Interbotix ROS toolboxes directory to make everything work. And the reason for that is because we don't want to have duplicate code, right? So we have Interbotix ROS Rovers that contain arms there are arms on the rovers, and then we have our standalone arms. So instead of having duplicate pieces of code in both those repositories, we have only one instance of that code in the toolboxes repository, and it just makes things a lot easier. And then finally, we have the application layer. So this would be like our Joy ROS package, the PID ROS package, the Puppet ROS package, any of our Python scripts. That would be more of this layer. All right. And that is it for the Interbotix ROS Manipulators repository. I'm going to go over to the turrets one. And since you've already seen what the directory structure looks like, this should go a lot faster. Interbotix ROS Turrets. So in this case, we have our Interbotix ROS Turrets part of this diagram highlighted, showing we're working with pan tilt mechanisms. I think we have 5 of those. So this is the high level, the first level directory. Right now we only have Dynamixel-based turrets. So that's why there's only one folder in this directory. But if we had another one, it would have its own directory. So click that. We have the same structure. In this case, we have an Interbotix XS turret control package, and that is responsible for, again, launching the SDK ROS wrapper that I wrote with and loading the correct motor config file to launch the pan tilt mechanism with the right names and default settings. We have an Interbotix XS turret descriptions package that has the same layout as in the ARMS repository, like a meshes directory for our different turrets. So, we actually have 6. So one of them is our vision kit. It's very similar to the Phantom X XL430 turret, but it has a life cam on top of it. So then we have the Gazebo ROS package that allows you to simulate the turret in Gazebo. So these are the core ROS packages because you would build on top of them. You wouldn't use them by themselves. So then some of the examples we have a object tracker ROS package. So this allows you to, this is specific for our vision kit for the PXXLS cam robot model, which allows you to track a object by color or by tracking the AR tag on it. Then we have the Interbotix XS Turret Simple Interface ROS package, which is used to, you can control a turret using a PS4 controller, or there's a GUI that is launched, which allows you to manipulate the turret that way. Besides for that, we have some Python demos. And here's some of our Python scripts that can be run if you don't want to use ROS and you're not familiar with ROS, you just want to work with, you're a higher level researcher and you want to work on your own research project without having to deal with the lower level ROS code. Okay, go back to this directory. So we also have an install here for loading, for installing all the code that is necessary. This is a bash script. Again, you look at the README and it'll tell you how to go about doing that. In this case, we don't have a cat can ignore file here because there's only Dynamixel-based turrets here. But if we were to add another type of turret platform that was based on a different actuator, so we would stick a cat can ignore file here, and you would add the other directory here with the other turret platform that works based on other actuators. And the bash scripts that I showed you in the install directory would have to be modified so that you would remove the appropriate cat can ignore file. Okay, so that's it for the turrets. Let's move over to the crawlers. So here we have our circular diagram again. The yellow one highlights which repository we're currently in, which is the crawlers. Same structure as before. We only have, pretty much like the turrets, right now we only have Dynamixel-based hexapods. So if you click on here, you're going to see the core ROS packages again, just like with the turret platforms. Control package that launches up the XS SDK node and loads the URDF to the parameter server. We have the descriptions ROS package, which has all the STLs. And okay, I think I said the control package loads up the URDF. It calls the descriptions ROS package, which loads up the URDF. Then we have the Gazebo package so that you can simulate the hexapod in Gazebo. Still have the install directory that allows, which is containing the bash scripts used to install all the software you need for the hexapod crawlers, and that's outlined in the README. We have our examples directory with our demo level ROS packages. In this case, we only have a joystick control option, and then some Python demos. Again, if you don't want to work with the ROS code, you can just use Python directly and treat the robot as an object. And the IRROS structure here is the same as before, U2D2, dynamic servos. In this case, we have, for our Hexapod platform, we have NeoPixels installed because it works off a Raspberry Pi. So the NeoPixels are connected to the GPIO pins. There's a module that allows you to interact with the NeoPixels that can be installed, and that would be in the driver layer. Even though we don't currently have a LiDAR on our Hexapods, this is something that could theoretically be put on there, and you would use the RP LiDAR ROS package to control it if you're using this type of LiDAR. For our PS4 controller, you can use the Joy package, but we're still using the same Interbotix XS SDK ROS wrapper. You're still loading the motor configs to the Dynamixel ROS wrapper here, and the Hexapod control launch file is starting up the Interbotix XS SDK ROS package. It starts up the NeoPixel ROS node that I created, and it also passes parameters to the Interbotix XS Hexapod descriptions ROS package, which loads up the URDF. And then in the Interbotix ROS toolboxes repository, we have a Hexapod IK solver module, which also is in charge of gates, and we'll get more into that in our last video. Then we have the application layer, which is the Python demos or the joystick ROS package, etc. All right, so moving on to the very last one, our ROS Rovers repository. So again, we have this image here. We're in the ROS Rovers repository. And in this, right now, we currently only have Localbot platforms. So if we go into this directory, we're not going to see any cat can ignore file because we don't need one just yet. But once we do add other platforms that are not based on Dynamixel servos, we would have to add a cat can ignore file here, and then edit the installation scripts appropriately to remove it, so that the cat can make command knows which ROS packages to install. All right, so we have our core ROS packages, the control ROS package. In this case, if you look into our IRROS flowchart here, it's not just the U2D2 with the Dynamixel servos. We also have the Kabuki base here in the hardware layer. We have, if you have the LiDAR equipped, when you purchase the Localbot, there's going to be the LiDAR on top. We're going to have the D435 RealSense camera there, and a PS4 controller as well, if you're going to be controlling the robot using that. We're still using the Interbotix XS SDK ROS package in the driver layer. We're going to be using the Kabuki node, which is already created by Eugen, to interface with the Kabuki base. The RP LiDAR ROS package is going to be used to control the LiDAR to interface with it. RealSense ROS package is used to interface with the RealSense D435, and the Joy ROS package is used to interface with the PS4 controller. And then our XS Localbot the Interbotix XS Localbot control ROS package, we're still going to be passing the motor configs to the Interbotix SS SDK ROS package. But besides for that, we're going to be starting up the ROS nodes to control the Kabuki node, the Kabuki base. We're going to be passing parameters and starting up the RP LiDAR ROS packages and RealSense ROS packages to work with the camera. And we're going to be passing parameters to the Interbotix XS Localbot descriptions ROS package to load up the URDF. And then we have the toolboxes level, and we have a custom Localbot module just for that. We again have that ROS control package. That's the same one that is used for the standalone arms. That is being used here. And a move it interface package, the same one that again was used for the standalone arms, is used here as well. So it's modular like that. And then we have a research level application here, which is Python scripts, or the joystick ROS package would be considered an end user application. Okay. So if we look here, we already mentioned this is a core ROS package. This is a core ROS package, as well as these two. This is also a core ROS package. It's all about doing navigation and SLAM on the robot. But this is something you would build on top of, right? So you would develop your own code in Python or in your own ROS package to do like frontier exploration, or for the robot to go to a certain place and pick something up. So that would be, you would build on top of that. Then we have the perception ROS package, similar to the one we had before with the arms. it gives you all the tools to pick something up, but you would still have to write the code to apply it for your specific project. And then we have the Interbotix XS Locobot ROS Control ROS package, which contains the config files and launch file to configure the ROS control node appropriately. And the ROS control node is housed in the toolboxes repository. We have our installation scripts to install all the code on the Locobot platform. We have our examples directory that contains our end user demo level ROS packages. So joystick, we also have a move an interface one that shows you how to move the arm on the Locobot to specific poses using the move group Python and C++ APIs. Then we have finally the Python demos, just like before, with different Python scripts you can use. It sits above the ROS layer, so if you don't know ROS, you're still good to go. Okay, and that is it for our robot level ROS packages. Thank you for watching, and I'll see you in our 4th video.